talked about sampling distributions, and that told us how mean values were distributed. And we found that in many cases, mean values, X bar values, sample mean values, are distributed normally, which leads us into statistical inference, and we find that we are able to construct these interval estimates that give us much more information than just a point estimate. And we talked about that last time. We were working on this problem where we said it would certainly be relevant to an airline to know the average weight of suitcases in the population of all suitcases that are loaded on a particular domestic flight. I can't measure that population. Those values exist past, present, and future. All right, no way I can measure that. But I can take a sample. So we talked about why do we want to know that. There is an important purpose to the study, estimating fuel usage, safety considerations, etc. So I take a sample and I find that when I look at 40 suitcases, the mean weight, X bar, because it's a sample, is 38.2. And we said that we're gonna start out assuming we know the standard deviation, because that allows us, we said when you know the standard deviation, you know that X bar is distributed normally, and that will allow us to calculate the confidence interval directly. We'll see after we go through this process that we'll look at the more realistic case where you don't know the mean, you don't know the standard deviation, you're gonna have to estimate the standard deviation along with the mean, and we'll see the central limit theorem does not hold. We're gonna have to use a different distribution, the T distribution. So we're starting out with this case. We want to determine a confidence interval for the population mean, the true mean weight of any suitcase on this flight. And we want to be 95% certain that our interval includes the true mean. We cannot be 100% certain because we're not measuring the entire population. All right, so those are fundamental ideas in confidence interval estimation. Is everybody clear on what we're trying to do? We're trying to get two numbers so that I can say I'm 95% sure that the true average weight of a suitcase, past, present, future, the true average weight is between these two limits, what I call the lower confidence limit and the upper confidence limit, two numbers. So we said we want to be able to make a statement like this. We already went through this. And we said because we know X bar is distributed normally, that our mean is going to look like that. It comes from a normal distribution, and my lower confidence limit and upper confidence limit are going to be those limits that I'm looking for, such that the probability is this shaded area, which is 95%. We can transform that to Z, and one of the last things we did in our last class was we said, okay, if I know all these probabilities here, and they're the same here, well, what would the Z value be? On the X bar diagram, those are the limits I'm looking for. When I standardize, those are gonna be Z values. Well, you should know by now from the computations we're doing, or if you don't remember, you can simply look up an area to the left of 0.025, and what would you find? Z equals minus 1.96. Or if you looked up an area, cumulative area of 0.975, the area to the left of this upper limit, you would find Z equals plus 1.96. So the Z values on confidence intervals will always be negatives and positives of each other. Confidence intervals are always symmetric around the X bar value that you've calculated. So those Z values It'll always be the same z-value on the right and on the left. For a 95% confidence interval, that z-value will always be 1.96. Do we always use a 95% confidence interval? Absolutely not. That's one of the biggest misuses of statistics, and we're going to talk about that a lot more when we get to hypothesis testing and we talk about risk when you're making statistical inferences. 95% confidence interval, a 95% confidence coefficient says you're taking a 5% risk that your estimate is wrong. There's a 5% risk that the population mean is really less than your lower confidence limit or more than your upper confidence limit. Is 5% too much? Well, that depends on what the application is. All right, we're talking about an airplane where they deal with safety factors, multiples of 4 and 5. Yeah, that probably, 5% is probably okay. On the other hand, if you consider that we want to estimate our annual fuel expenditure, and I don't want to be off by 5%. I don't want an error rate of 5%. I make too many important decisions based on this interval. Well, you shouldn't be using a 95% confidence coefficient. Maybe you'd need 99%. We will see that, and it's unfortunate because every textbook problem you look at, it's either 90%, 95%, 99%. Why? These numbers are different. The results are different, and they have very important interpretations. Very important to think about how much of a risk are you willing to take. If you're willing to take a 10% risk, you're going to get a nice, precise interval with very little certainty. If you want much more certainty, much less risk, if you want a 99% interval, that's going to be a much wider interval. You're going to have less precision. It's always a trade-off. With a constant sample size, you get a fixed amount of information. You get to choose how you use it based on a realistic assessment of how much risk you're willing to take. So I just want to mention that. We'll get back to that a lot because it's a big problem in the fact that people will just, okay, we'll use 95%. In many industries, that is a standard. In polling, that's a standard. All right? That's fine. If it's a standard, then it's wrong to use other values. And there was a case years ago with a stent made in, I can't remember the name of the company in Boston, that made a medical device. And on all their results, they used a different confidence coefficient to report the effectiveness. Now, in that industry, there were commonly understood metrics that were used, values of what we call alpha. They used different ones that made their results look very, very good, but they didn't really report what they were doing differently. And so if you didn't look at what they had actually done, based on results alone, their device was much more effective than anyone else's. Well, not if you use the standard measures of confidence level. So very important to use that appropriately. So we'll get back to that. Here we're using 95%. So what do we know? Because of the normal distribution, I know the z-value will be between minus 1.96 and plus 1.96 95% of the time. So this is something we're all familiar with. We've looked at this. If you look at a table, you can write this statement. All right? Now, that's not what I want. I want a statement that looks like probability I want two numbers lower confidence limit, upper confidence limit, two numerical values, such that the probability that this unknown population mean is between these two numbers is 95%. That's what I'm looking for. So how do I get from that statement, which we know, to this statement? Well, let's look at what we can substitute. We know that for a sample mean, for the distribution of the sample mean, I know that Z equals X bar minus mu over sigma sub X bar. All right, we just went over that on the homework, so we're familiar with that. Well, now it's just a matter of rearranging these symbols arithmetically. I have an inequality. I want mu in the middle. So the first thing I'm going to do is I'm going to multiply all three parts of the inequality by sigma sub X bar. That's going to give me minus 1.96 sigma X bar plus 1.96 sigma X bar. And what am I going to be left with here? X bar minus mu. Then I can subtract X bar from all three parts, and that's going to leave me with minus mu in the middle. But I want mu in the middle. So who remembers what happens when you have an inequality and you multiply through by a negative number? I want mu instead of minus mu. I'm going to multiply by minus what? Yeah, what happens?
Well, reverse.
You reverse the direction of the inequality. Good. All right? So I'll do all that algebra, all that arithmetic. I'll reverse the direction of the inequality and then rearrange it so that what it looks like is X bar minus 1.96 sigma X bar is less than or equal to mu, is less than or equal to X bar plus 1.96 times sigma X bar. And that probability is 0.95. That's exactly what we're looking for. The probability is 95% that mu is between those two numbers. And what do we know about those two limits? I know X bar. If I take I have to know X bar. 1.96 was the Z value. I looked that up in the table when I told you there's a confidence coefficient of 0.95. We drew that normal distribution, so I was able to find the Z value. And I have to know sigma X bar. It's sigma over the square root of n. So the number on the left and the number on the right, I can calculate. Those are numerical values. They're not variables. They're not unknowns. Those will give me the two confidence limits that I'm looking for. So what we can say, and this is where we ended last time, the probability is 95% that mu is between X bar minus 1.96 times sigma X bar and X bar plus 1.96 times sigma X bar. Any questions on what we're expressing?
Why is X bar not negative when you?
Why is X bar what?
Not negative when you, I guess I'm assuming you solve that problem.
X bar can be negative or it's whatever it is. If I'm average, it's the sample average. So if I'm averaging a bunch of negative numbers, yeah, X bar would be a negative number.
Meaning if, whether X bar is negative or positive, why isn't it negative in the formula?
Why isn't it minus X bar? Because then it wouldn't be a confidence interval around mu. In other words, I just did algebra to get what it is, to get, that is what it is, do the algebra. Multiply by sigma X bar, subtract X bar, then you have to multiply by minus 1 to get mu instead of negative mu. That's going to take away your minus X bar to make it plus. Any other questions?
So, in the problem statement, Professor, they gave the standard deviation for the suitcase cases also. So that's not going to help us actually. It's even to example.
Oh, it is going to help us. That's sigma.
Oh, yeah.
And I can get sigma X bar from sigma as sigma over the square root of n. Okay?
So if, like I'm trying to apply it in realistic
Yeah.
scenarios, right, like you're trying to find what, like, no matter what sample I'm gonna take, my
Mhm.
average suitcase weight should fit into the deviation.
Right.
Data points, right?
Mhm.
And for this information to be calculated, you need to know the standard deviation of the population.
Which we have.
Right, typically, do we have that
No.
information?
We have a sample, we can calculate a sample standard deviation, S, but then I can't use the normal distribution. We'll talk about that after. What we're talking about now is calculating a confidence interval when sigma is known. Realistically, no,
No.
we don't, we'll get to that. Okay, and we'll see under certain circumstances, we can use this anyway. Yeah,
When you're using the sample, like in the book, it gives you the mean or whatever it is, mu, but.
oh, it doesn't give you mu,
No,
not
I-
confidence intervals, that's what we're trying to estimate.
I know, can you let me finish? I'm saying, in the book, they're giving us an example, and they're telling us what the mean is. In your case, you're saying we won't know it. How do you know you have the right sample?
You don't, you know that you're 95% certain. It's not that you have the right sample. If you picked a random sample, you have a right sample. There are hundreds, thousands, millions of possible samples depending on the population size. You pick one, and if you've selected it randomly, you have a right sample. It may not be a representative sample, that's the risk we take in sampling. So we don't know. What do we know? We're 95% sure that we have an interval for mu. There's a 5% risk that we're wrong, because we happen to pick the n smallest values in the population, or the n largest values in the population. Do we know that we picked the n smallest value? How could we know? We've only measured those sample values. I don't know what the rest of the population looks like. That's where the risk comes from. If not for that, yes, I would know that the mean is in there. I can never be 100% sure.
Also, are there guidelines on what is the right sample size
Yes.
for the population?
Yes, yes. And I'll talk more about that later, because we have to have some sense of what happens when you change the sample size. But you'll see in that chapter, there's a whole section on selecting the sample size. You need to make some subjective decisions about how precise you want the interval to be, and how low a risk or how high a risk you're willing to take. Once you make those decisions, you can calculate the necessary sample size. All right, so, and I'll talk about that once we get into precision and risk a little bit more. But yes, there are definite guidelines. There are formulas based on the normal distribution that allow us to do that. Okay, so we can say in general, X bar minus 1.96 sigma X bar and X bar plus 1.96 sigma X bar are 95% confidence limits on the population mean. All right? Well, that's fine, except we're not always willing to take a 5% risk of being wrong. We're doing this because we're going to use these results, so we want to be sure that the risk that we take matches what we're willing to take. So, in general, we say that the probability that mu is between two values, the lower confidence limit and the upper confidence limit, is 1 minus alpha, where LCL is the lower confidence limit, UCL is the upper confidence limit. 1 minus alpha is the confidence coefficient. It's what I'm using 0.95 to represent for this problem. Alpha,
Sorry, can you go to the previous page, Professor?
yeah, let me just finish this page, okay? Alpha, or 1 minus alpha times 100% is what we call the confidence level. Alpha is what we call the risk. The risk that our interval does not include the population mean. All right, here's the last slide. So, what we have on the next slide that we just looked at is a general formula for finding a confidence interval. or general representation for finding a confidence interval. What we're gonna look at next is what's that general formula. Okay, so it doesn't have to be 95%. It could be 99, it could be 90, it could be 92%. We're gonna have to make that subjective decision for the particular system that we're dealing with. And for those of you that are doing presentations on confidence intervals, this is something you need to think about for your particular system. How much of a risk are you willing to take? So when sigma is known, we can calculate a 1 minus alpha percent confidence interval by taking x bar minus the z value. Remember, we just used 1.96 because we were talking about 95%. If I use a different confidence level, I'm gonna have a different z value. We had x bar minus 1.96 times sigma x bar. More generally, I have x bar minus z, and instead of sigma x bar, I wrote sigma over the square root of n. That's how we calculate sigma x bar. So mu is gonna be between x bar minus z times sigma over the square root of n and x bar plus z times sigma over the square root of n, with probability 1 minus alpha. And how do we find this z value? Same way we found 1.96. It's called the critical value. And we use the z value that corresponds to an area of alpha over 2 in the right and left tails of the distribution. So if you remember, a couple of slides ago, we had a picture that for 0.95, for an 1 minus alpha of 0.95, this was 0.025, this was 0.025, and using those values, alpha over 2, 95%, 0.95 is 1 minus alpha, alpha equals 0.05. The z value for alpha over 2, for 0.025, was the way we got 1.96. It's the way we're gonna get the z value for any confidence level, or any confidence coefficient. So let's now look back at our suitcase example. Any questions to this point?
Professor, what are the assumptions we're making about the population? That it's normally distributed, or?
No, we don't have to, because we know sigma. All right, when we know sigma, when we don't know sigma, we're gonna have to make the assumption that it's normally distributed, and we'll have to use the t-distribution. All right, here we know sigma, so the sampling distribution is going to be normally distributed. So, in our suitcase example, if you look back at the problem, the sample mean was 38.2, the standard deviation sigma was 8.52. What do I have to do next? Say it again? Sigma sub x bar. Standard error of the mean, standard deviation of the sampling distribution. That's going to be sigma over the square root of n, 8.52 over the square root of 40, or 1.35. What else do I need? I have x bar, I have sigma x bar, I just need z. But we said this is a 95% confidence interval. So 1 minus alpha is 0.95, alpha is 0.05, and alpha over 2 is 0.025. The same thing I wrote on the board. So what is Z? Or plus 1.96, either way. We're gonna subtract it for the lower limit, we're gonna add it for the upper limit. So let's now find the confidence interval. We have everything we need. The lower confidence limit is x bar minus z times sigma x bar.
You have 1 second, let's go. Okay, thank you.
I also need it, sorry, the lighting is causing. Okay, I have it.
Everybody ready?
No.
No.
Yes.
Okay, so now we're ready to put all this together. We have everything we need, x bar, sigma x bar, and z. We know that the lower confidence limit is x bar minus z times sigma x bar, 35.56. The upper confidence limit is x bar plus z times sigma x bar, 40.84. So I can now make the statement that the mean suitcase on this flight, the population mean, population average weight is between 35.56 and 40.84 with probability 95%. We're 95% certain that the true average weight of a suitcase is between those two values. So does that seem like a reasonable estimate? What would make it a reasonable estimate? What am I asking you to judge when I ask, is this a reasonable estimate? We've talked about the purpose of the study. It's a matter of safety considerations. We don't want to exceed the maximum allowable weight. It's a matter of estimating fuel usage, estimating potential revenue from alternative sources like cargo, taking on non-passenger cargo. All right, so those are the kinds of things we use it for. Is this useful or not? What would make?
Depends on the tolerance, risk tolerance.
Okay, so the first thing is a level of risk of 5% reasonable? I don't know, I'm not an airline expert. That's a subjective decision. I have to ask a subject matter expert. I have to say, is it okay to be 5% off? Well, what does being 5% off mean? It means there's a 2.5% risk that you're gonna actually have, your average is actually less than 35.56. What are the consequences of that? Well, you could have taken on more cargo. That's lost revenue. All right, you know, now you know the probability, 2.5%. You can estimate the amount of additional revenue you might have had if you had realized that. Now you have a measure. Same thing on the top side. There's a 2.5% chance that the average weight is above 40.84. Well, now I'm talking about safety considerations. Is that a safe level? What are the guidelines? what are the actual specifications for total weight of cargo? Am I willing to take a 2.5% risk of being beyond that? So these are subjective questions. We're doing the math, but that choice of a 5% risk is not an arbitrary choice. That's something that should have been determined by talking to the subject matter experts. All right, and presumably 5% is okay. But it's important that you understand that that number doesn't just, it's not just an arbitrary choice. That comes from an understanding of the system. So one issue that we know, when I say, is this a useful interval? I know it reflects a risk of 5%. Presumably that's okay. If it's not, I better go back and recalculate for a different alpha. What else is relevant to whether it's useful or not in this statement? So suppose I did this calculation and I said to you, I collected different data, and I said to you, my result is the probability is 95% that the mean weight of a suitcase is between 20 pounds and 90 pounds. Would that be okay?
No.
No, why not? What's wrong? I still have only a 5% risk. Go ahead.
But
What's
then
wrong with it?
But then if you say it's 5%, so you're doing like 2.5 on both sides, right? So 20, less than, like that would be 17.5%.
No.
Standard
It's
deviation.
divided.
No, you have
The
to
range
find
is-
the standard deviation.
Can we have one person at a time? What you're doing is you are taking 2.5% on the probability, not on the values on the axis. In other words, the weights themselves, you're not subtracting 2.5 pounds. It's the weights are on the x-axis, it's the probability.
Yeah,
So
the range is too wide then.
the range is too wide, exactly. Of what use is it to know that the average weight of a suitcase is between 20 and 80 pounds? I didn't have to collect data to tell you that, and I'm not an airline expert. That's not a useful interval because it lacks any precision. When I'm talking about precision, do I want a narrow interval or a wide interval?
Narrow.
If I tell you, if this result had been, the probability is 95% that the mean weight of the suitcase is between 35 and 35.1 pounds. Is that a good confidence interval? Is that a good estimate?
Yeah.
You can't get much better than that. Basically, you know exactly what the average is for the population. You have almost perfect precision. The narrower the interval is, the more precise. So what we would like, of course, is low risk, a high confidence coefficient with very low risk, and a very narrow interval, a very precise interval. The bad news is that you can't do that with a fixed sample size. With a fixed amount of information, it's a trade-off between level of certainty or risk and level of precision. We'll see in a minute. You want less risk, you want more certainty, you're getting a wider interval. You have a fixed amount of information with a fixed sample size. You want to improve both your precision and your level of certainty, you have to increase your sample size. You have to get more information. You don't get anything for nothing. You cannot improve both the risk and the precision with the same sample size. The best you can do is figure out what you want, which is generally the maximum risk you're willing to tolerate, and you have what you have. You want more, you need more information. So, is this a good interval? That was my first question. Well, we said presumably a 5% risk is okay, but I'm not the one to determine that. A subject matter expert is. And presumably this 5-pound range is precise enough for their purposes. Again, I gotta talk to somebody who knows what they're doing with this. I'm just telling them what they have based on their sample of 40 suitcases. I'm not necessarily telling them what they wanna know. So we need to know from a subject matter expert, what are the limits on precision, what are the limits on risk, based on an understanding of the system. So let's first look at how do we do this using Excel? Because Excel does confidence interval calculations, not completely. They do a piece of it in the following way. It doesn't do the whole computation for you, but it does calculate that Z times sigma X bar. And you don't have to look up Z and you don't have to calculate sigma X bar. In other words, from the data you're starting with, your lower confidence limit is X bar minus Z times sigma X bar. Well, that's what Excel calls confidence dot norm. And it's a function of alpha, the risk, the standard deviation of the population, and the sample size, N. And it'll do the calculation of Z times sigma X bar. The upper confidence limit is gonna be X bar plus this confidence dot norm of alpha times the standard deviation times the sample size. So for the example we just did, what's alpha? 0.05, good. And what's the standard deviation that we're gonna type in here? Good, it's the population standard deviation, 8.52. It's not 1.35. And N, of course, is 40. So this is what we have from the problem statement. Alpha is 0.05, sigma is 8.52, N is 40, X bar is 38.2. So that's all information that was given to us in the problem. We use that to calculate manually the confidence interval. To do it using Excel, I'm gonna put in these two formulas. The mean, 38.2, minus confidence dot norm, alpha, sigma, and N, 0.05, 8.52, and 40. Any questions so far? Yeah.
Another question on the earlier statement you made. You said to decrease the risk and increase precision, you have to take, like you got a certain range for your confidence intervals, right? And if you want to decrease the risk and increase the precision of your interval, were you saying you have to increase the sample size or should we take more samples?
Oh, okay, that's an important question and not one we're dealing with here. What I'm saying is you need a bigger sample size, right? If you want more precision, if you want a narrower interval with the same alpha, you're gonna have to take a bigger N. Now, what you're asking is a question on sampling technique. Should we just add to this sample or should I take a different sample? All right, we're not getting into those intricacies of sampling. That's what I mentioned last time. You know, if you take market research, you'll talk all about that. What we're assuming is that you would just take additional items so that you had a total sample size of 100 or 200. You asked before about are there any guidelines, and I described that there's an equation you can use to calculate. That's the whole point. If I decide my risk is 5%, that's okay, but I want my interval to not be 5 pounds wide, but only 2 pounds wide, that's one of the quantities that goes into that calculation. So I can calculate that formula for sample size, for the necessary sample size, would be a function of the risk you want and the precision you want. And that'll give you a number bigger than 40. And so now your question about, okay, how do you get that? Do you throw out everything and take a new sample, or do you just add to get to that number? And we're talking about, you know, a sample of the larger size where you would just take additional suitcases from that flight. Okay? Yeah.
One question, you know, I understand the formula, right, but in reality, right, we will never be able to really calculate the sigma, right, the population
Yeah,
standard
we're gonna
deviation,
get to that.
right, so,
We don't have sigma in the real world.
in real world.
In the real world, I'm gonna have to take those same 40 suitcases and calculate
The
S.
sigma, okay.
But that's gonna change things under certain circumstances. We'll get to that, all right? We introduce it, and you see the book does the same thing. I mean, any book you look at does the same thing. We start out with the assumption of the central limit theorem to illustrate the process. Then we talk about, okay, what if you don't know? I mean, sometimes it's reasonable to conclude that you have a long enough history and it's a stable process. It doesn't vary very much. So you use your historical estimate as sigma.
Right.
And that's the assumption we're making here. But in reality, you're right. You normally don't have sigma. We'll get to that. Okay, so if I set up the spreadsheet, so I put in alpha, I put in sigma, n, and x bar. And here's my formula. My Excel formula equals the mean, which is in B6, minus confidence dot norm of alpha, sigma, and n. And the upper confidence limit is B6 plus confidence dot norm of alpha, sigma, and n. And numerically, 35.559, 40.840. Same thing we got. All right, but when you do it with Excel, you don't have to calculate Z, you don't have to do the computations. All right, there's nowhere in here where I had to put in 1.96, and Excel doesn't tell me, or the way I've written it, Excel doesn't tell me it was 1.96. Any questions on that, on how we would use Excel? All right, so now, let me ask the following question. I get this interval, and I say, you know, 5% risk is too much. That was wrong. I'm not willing to take a 5% risk of being wrong. The cost of that, the consequences are too high. I'm gonna miss 2.5% of the opportunities to get more cargo on, for which I earn extra revenue. I'm gonna miss 2.5% on the safety and fuel end, where I may not have enough. I don't want my risk to be 5%. I'm only comfortable with a risk of 1%. I don't wanna take more than a 1% risk. So what kind of confidence interval are we talking about?
99%?
99% confidence interval. So that's gonna be much lower risk. Now the question is, what is that interval gonna look like? Right now, so for 95%, this was 0.025, this is 0.025, this is 35.5, and what was the other one, 40.8. All right, now I want a 99% interval. So where's my lower confidence limit gonna be? Is it gonna be to the left of this or to the right of this?
Towards me,
This is 0.95. If I want to enclose 0.99, I gotta go out more. 0.99 is bigger than 0.95. So these limits are gonna be further out. Here's 35.5 and here's 40.8. The limits are gonna be further out. How do you know? X bar is the same, sigma X bar hasn't changed. What does change?
Alpha.
Well, alpha changes, yeah, this is 0.005, and this is 0.005, and because alpha changes, what else changes in the computation of the confidence interval?
Z.
The Z value, good. This Z was 1.96 minus 1.96 and plus 1.96. What are you gonna get here if you wanna be all the way out at an area of 0.99? It's gonna be a bigger Z and a smaller negative Z. Can somebody tell me what it's gonna be? If the area is 0.005, if alpha is 1,
It's 3 sigma, right?
no, not 3 sigma.
Minus 2.57?
Yeah, it's actually 2.575 or 2.58, I rounded up. Yep, good. Good, what do you look up? You look up an area on the left side of the table of an area of 0.005, find the closest Z value. It's minus 2.5, it's right in between 2.57 and 2.58. If you look up an area of 0.995, on the right side, you'll get the plus Z, the same number. Well, if the confidence interval is X bar minus Z times sigma X bar stays the same, sigma X bar stays the same, but you're multiplying by a bigger number, what's gonna happen? Your lower confidence limit is gonna be lower, your upper confidence limit is gonna be higher. What does that tell you about the precision? It's worse. Now we're getting closer to the, 20 to 80, the useless information. Because you still started with the same amount of information, your 40 data points. You wanted to improve your risk. You wanted to lower your risk. You don't get anything for nothing. You want less risk, more confidence, you're gonna have less precision. You can't have both. The only way you could have better precision and lower risk, expand your sample. So let's look at the actual computation. I mean, the important thing is that you understand what we expect to see right now. So we want to be 99% certain, and nothing has changed as far as our data. We still have a sample mean for the 40 suitcases of 38.2 and a standard error of the mean of 1.35. We said that if we want to be 99% certain, so alpha is 0.01. So the two areas in the tail are each 0.005. And we looked it up in the Z table and found Z equals 2.58.
So with the 2.58, that was just looking up the 0.005, correct?
In the table, right. You look up an area of 0.005 and you get a Z of 2.5.
I have a question.
Yeah.
So from the table it says 2.57 is 0.0051 and 2.
Yeah, it's right in the middle. It's-
And 2.58 is 0049. So which one should we
It's
take?
right in the middle. The exact Z value is 2.575 as it happens.
Okay.
For our purposes, it's fine if you round off. If you use 2.57, it would have been fine. If you use 2.58, it would be fine, because it happens to be right in the middle. If you use 2.575, as Excel is going to do, that's gonna give you a more exact value. All right, for our purposes, this is fine.
I'm struggling with finding it myself.
All right, that's something, that's the same thing we've been doing for the last 3 weeks. You go to Z, you look up the area that's closest to 0.005, somewhere you'll find an area on one of those two pages that's closest to 0.005. When you go to the left, you'll find it's 2.5, and when you look at the column above it, you'll see 0.8.
You're looking at the percent in the middle, not the.
All right, so, did you find it now?
Yeah, cause I was looking, I have to look at the middle, I always make that silly mistake.
Any other questions on how we get any of these numbers? Okay, lower confidence limit, X bar minus Z times sigma X bar, upper confidence limit, X bar plus Z times sigma X bar. And we get 34.72 and 41.68. What do you notice? It's wide, as we expected. For a fixed amount of information, it's always a trade-off between precision and certainty. Our level of certainty got better, it went from 95 to 99%. Our precision got worse, we went from a narrower to a wider. But comparing the values themselves, did it get a lot worse? Really a negligible difference, but we got to improve our confidence level by a lot. So we see it's not a linear relationship. I mean, obviously it's a function of sigma X bar and the particular level of certainty you want. So if we look at this, we may decide for practical purposes, yeah, I haven't given very much up and I've lowered my risk dramatically from 5% to 1%. This is a much better interval. If the numbers were such, if the variability were high enough that it would have become a much wider interval, we might come to the opposite conclusion, that we're willing to accept more risk so that we can get better precision. Yeah,
Just so I can just clarify.
just that she had her hand up first.
Sorry, so I guess the one thing, so when I found it on the E.2 table, it was technically negative, right?
Yeah, well, in one case, on one side, we're taking X bar minus Z times sigma X bar. In the other case, we're taking X bar plus Z.
Correct.
So you're always subtracting a Z value on one side, adding a Z value on the other. So it really doesn't matter whether you're looking up the negative or the
You
positive.
should always just.
You're
look
getting
at
the Z
positive.
value, yes, and you subtract, you take the negative from X bar on the left side, the positive added to X bar on the right side, to the other. Yeah, somebody else? Yeah.
I'm just making sure I'm interpreting this right, so you're saying it's less precise because the range is bigger?
This is wide.
Okay,
Exactly, that's what we mean by precision.
okay.
Question,
Yeah.
so, if the risk is lesser than the,
I'm sorry, so if the
I mean,
risk,
if the risk percentage is less,
that's better.
that's better, right? But here the range kind of like this widens, if the risk is,
It's always gonna be the case. The risk went from 5% to 1%, that's better. The width of the interval is wider, that's worse. You can't improve both with a fixed sample size. With the same amount of information, it's a trade-off between risk or certainty and precision.
Yeah, but I mean, if you think of it, it's just basic logic as well. I could be 95% sure I'm gonna fall within this range, but I could be 99% sure I'm gonna be within a little bit of a wider range.
Exactly. The more certain you wanna be, the more values you have to include.
So,
Yeah.
it's in summer, so risk is less, right, because it went from 95 to 99, but now.
The level of certainty went from 95 to 99, so the risk went from 5% to 1%. The risk of being wrong.
Correct.
Mhm.
Why is a wider range worse though? I don't understand.
Well, let's think about the extremes. I wanna know the average weight of a suitcase so that I can make a decision. Let's pick simply, I wanna know how much fuel I have to carry. If I tell you the average weight of a suitcase is between 35 and 35.1 pounds, You know that the average, if there are 10 suitcases, I'm carrying 350 pounds. If there are 1,000 suitcases, I'm carrying 35,000 pounds. All right? Now I tell you, well, I calculated a different interval, and the average weight of a suitcase is between 10 pounds and 1,000 pounds. What does that tell you?
Nothing.
No.
Think about it like this.
All right, so excuse me, let me finish, please. So the idea is that when you have a wider interval, you have less information, you have less precision. That's what we mean by precision. Okay, so is that clear?
I
Yeah,
believe
go
so.
ahead. James, you had something to say?
No, I was gonna give him an example of it.
Okay.
So,
Yeah.
so if we still increase the sample size from 40 to 80, for example, here,
Right.
the range doesn't change that much.
Oh, wait a second. If I increase from 40 to 80, oh, and you're saying keep alpha at 0.05?
Yeah.
Yeah, you'll get a slightly narrower range. We see the precision is very insensitive, is not very sensitive to changes in alpha, right? What did we find? We reduced the risk from 5% to 1%. We hardly changed these at all. Now, the change was in the direction that we expected. All right, something went wrong if we wound up with a narrower interval here. It is wider, but it's wider by a negligible amount. So yes, if I changed n from 40 to 80, you'd see the same thing, the precision in this case, because the standard error is very small. That 1.35 is a very small standard error. So even if I doubled my sample size, I wouldn't gain all that much in precision. You know, what we have in this case, because of the numbers, is something that's much more sensitive to alpha than to precision. Any more questions or comments on this? All right, so being able to do the arithmetic, that's the trivial part of it. Understanding how to interpret a confidence interval is the important part. I mean, that's why we're talking about it and going over that over and over, that relationship between risk and between precision and level of certainty. What does that mean? What's better precision? What's a better level of uncertainty? And the fact that it's a trade-off. Yeah.
So Professor, in a real life example, right, typically a sample gives an indication of what your potential universe will
Sure.
look like, right?
Well, you hope so.
Yeah, you hope so, right? So you pick your sample, you have your mean, standard
Right.
deviation, all that calculated, and is the risk of determining if it is 99, 95?
That's
Is it
not based on your
sample at
sample.
all?
No, that's based on what you know about the process. In other words, let's say I'm measuring, I have a manufacturing process and I want a confidence interval on the amount of active ingredient in a pharmaceutical product. Okay, obviously a very critical issue. All processes have variability. So you're supposed to have 10 milligrams in every capsule. You don't have exactly 10 milligrams in every capsule of any manufactured item. There's some variability. All right, what we want to know is what does that interval look like with a given level of risk? How do I decide whether I want to look at a 90% interval or a 92% or a 95 or a 99? I gotta ask somebody who knows something about this product to tell me what's the ramifications of having too little of the active ingredient or too much of the active ingredient? What are the consequences? If I have too little, it's not effective. Well, that's a pretty big consequence. If I have too much, it's toxic, an even bigger consequence. So in that case, what I want is a very low risk, a very high confidence coefficient. I want to be 99.5% sure that I'm really including that mean. And I want low precision. I'm sorry, not low precision, I want high precision or as narrow an interval as possible, depending upon where that ineffectiveness threshold is and where that toxicity is on the other side. So those decisions are going to be made, not by me, not by the person doing the calculation, but by somebody who understands the process, who can say to me, I don't want more than a 0.01% risk. And I want that interval to be no more than 1 milligram or 0.5 milligrams on either side. Well, then I would figure out what sample size I need to guarantee that, and then I would do the computations. All right, so those are subjective decisions, and that's very important. And I keep repeating that because they're not subjective in textbook problems. You have to have a value of alpha. You have to be told what alpha is. You need to know the margin of error to calculate the precision. But deciding what values you want to use is really a subjective decision based on the application.
I think the risk is a critical decision.
Yes.
You have to take, I was thinking some data analysis will help determine this also.
Well, yes, it would, but the idea is that you want to also be sure you're following the scientific method. You don't want to look at your data and formulate your hypothesis from the data. You might have picked the smallest sample of 40 suitcases or 100 capsules. You don't know that. So you always want your decisions on those parameters to be based on what you know about the system, not the numbers that you got on one random sample. All right? I mean, that's the scientific method, is you collect your data after you formulated your hypotheses based on the observations. So yes, knowing what the data looks like helps you to make those decisions, of course, but we want to make those decisions based on our understanding of the system. Yeah.
So in that case though, we're saying it was, right, we chose to use very low risk, right, to get higher precision.
Yeah.
And a high confidence interval.
No, it's not, there's no such thing as a high confidence, a high confidence level, yes,
Yeah,
yes.
based on that.
Yes,
Just
correct.
problem that you talked about the manufacturing piece.
Correct,
Okay.
right, yeah.
So, I'm just trying to understand, where would we have sigma if we don't have mean?
This is the same thing I've been saying since we started this. We don't. It was an assumption, because if you don't have the mean, you probably don't have sigma.
Correct.
Sometimes you do, because you have a long history of this data, and there isn't a lot of variability, so we call it a stable process, and we assume that the standard deviation for the last 20 years of data is the population standard deviation. Realistically, in most cases, we will not have sigma, and therefore we'll have to change this procedure a little bit. And we're going to do that when we finish this. Right now, we are making the assumption so that we can talk about how you calculate a confidence interval. We're making the assumption that we know sigma. And as I've said, that's not realistic. In most cases, we will be using a t-distribution, but as we'll see, under certain circumstances, those values are the same as the z values. So we're going to get to all that.
I'm just trying to apply it back to the business.
Yeah, I mean, that's what we've been saying, it's not realistic. That's what I keep repeating, that no, if you know sigma, why don't you know the mean? Why are you doing this? So no, it is not realistic to not know the mean, but know sigma. But sometimes we do, because we're using past history. And if you have a process, you know, there's two characteristics of any process where you're measuring some parameter. There's the target value, the number of milligrams you're supposed to have in each capsule, the weight that's safe, ideally, and there's the variability. Those are two important characteristics. So what we're saying here is that the variability is very consistent. It doesn't change very much. How do I know that? Because I have a long history of data. It's the target value that's changing. In a case like that, it's not unreasonable to make the assumption that sigma is that your estimate of the standard deviation from that long history is the population standard deviation. If you have a stable process that doesn't vary very much, you're not going to have major errors in making that assumption. So that's also part of the justification for going through this kind of computation. But we will talk about what do you do when you don't know sigma. All right, that's our next step. So, we just found, we're 99% sure that the average weight of the suitcase is between 34.72 and 41.68 pounds, and we pointed out this is a wider interval. So, with the same amount of information on the 40 suitcases, we have more certainty and less precision. So there's a bunch of readings on this and a lot of them deal with the issue that the accuracy of your interval estimate depends on the accuracy of your measurements, obviously. All right, if there are errors in the way you're measuring the individual weights and therefore X bar and therefore inaccuracies in the way you're using the standard deviation, you're going to get results that are not accurate. So related to this example, there was an article from 2019 about Southwest Airlines. Anybody want to tell us?
Can we just, sorry, can we talk about the risk here though? So in the
Okay, what do you want to know?
So we said wider interval, more certainty, less precision.
More certainty means less risk.
Okay, thank you.
So what happened with Southwest Airlines? Okay, I hope you, at some point, the readings are most helpful when they fit into the material. You should be, at this point, done with the readings on confidence intervals and ready to start the hypothesis.
It's about the fueling thing.
Yeah, what they do.
Yeah.
It wasn't fueling, it was the weight on the plane. And what did they do? And why did they run into trouble?
Because they didn't have like an automated way to track the weight of the baggage.
Yeah, they were recording the data manually instead of using a scanning operation to weigh everything. They were using manual recording, and there were lots of mistakes, as there always are when you do a process like that manually. So they had a very inaccurate recording of the weight distribution between the front and the rear of the cargo bays. All right, that's a big issue. So, I mean, it was big enough to make the Wall Street Journal. All right, there's a problem in the way the data is collected that's going to affect any estimates of the total weight. And the article was about the miscalculation in the estimate of the total weight. In April of 2020, right near the beginning of the pandemic, there's an article about the COVID death rate and the problem of estimating the percent of infected patients that will die. And the problem was with the different ways of measuring. So for example, if you take the ratio of number of deaths over number of known cases, very difficult at that time in particular to measure either that numerator or that denominator. It was the denominator that was most inaccurate. And if you recall all the issues about how we were measuring these numbers, the number of known cases, initially at least, was very accurate. The hospitals weren't necessarily reporting, the cause of death accurately at the beginning because there were a lot of unknowns. Testing, remember, by April 17th of 2020, we weren't doing testing. It was symptomatically at that point. So there were a lot of cases that had never been reported. There were asymptomatic cases that were never reported, that no one ever knew about. So the article talks about the difficulty of estimating, for example, the mortality rate if you have these inaccuracies in the denominator. And in fact, they said that for a time, the impression was that the calculated death rate was an overestimate because it only included ultimately those people who were tested rather than everybody in the population who may have had it. Around the same time, in April of 2020, in AP News, confidence interval on the number of deaths, and you got all different results based on different ways that the data was measured. By September of 2021, last month, confidence interval on the actual number of COVID deaths, taking into account the reduction in other deaths, because remember what we didn't know in April of 2020, when these other estimates were made, we didn't know that there'd be far fewer cases of the flu, far fewer deaths from the flu than there normally are in a year. We didn't, you know, and there's a lot that's been written about the appropriate measure really should be the differential death rate, because while of course there have been over 700,000 deaths due to COVID, there has been a substantial reduction in death from other causes. So this article in The Economist talks about unreported deaths, increases due to other causes, all the people that had heart attacks and couldn't be treated because the hospitals were overwhelmed initially. And it's a very detailed article, and it has links to the methodology. You know, so it should give you a very clear picture of what these problems are, how measurement problems affect estimation problems. Another issue in confidence intervals, the margin of error sometimes isn't specified, and this is what I mentioned before, where I said that there are certain standards in certain industries. So sometimes, very often in financial forecasting, a wider confidence interval is used. Why? It's less precision, but it gives the company a lot more breathing room. If you forecast a wide range for financial performance, you're going to be right a lot more of the time. If you forecast a narrow range, nobody's going to be very impressed by the fact that maybe you have a high level of certainty, except you're probably not going to fall within that interval. There's too much uncertainty in the market. So with narrow ranges, analysts react much more to mild deviations from the midpoint. With wider ranges, they're less likely to be criticized. It's more likely that the value will fall somewhere in that wide range. So that was not one of the readings, but that's, you know, that is a truism about using confidence intervals, and that's had a lot of impact in how financial managers use forecasting.
Professor, wouldn't, in this case, because I read this article, wouldn't the data somewhat be skewed? Because
In which article?
This article with the COVID in September, right?
The last one we talked about, yes.
Because the data is somewhat incomplete, right? They were suggesting that even some of the deaths, they didn't take a test, therefore they couldn't truly determine whether it was.
Absolutely, that's what we're saying. That was what I was talking about with that denominator before being so uncertain. All of these articles about COVID make that point, that because you don't have precise metrics for measuring it, you don't get great results. You know, your results, either they're not going to be precise or you're not going to have a great deal of confidence in them. That's the problem. The problem is a measurement problem. In Vox, in July of 2019, the doomsday prediction. So, what did that say? What was that talking about with respect to our estimation problems? What was the point of that article? Well, it's an interesting article. You should read it. It's a discussion of whether it's possible to predict everything. Can you assess probabilities of unknown events? Can you assign a level of confidence to future events like the end of humanity? How do you apply these concepts to questions like that where you have relatively little information? Yeah,
When in there, wasn't his range so large that he thought it couldn't?
exactly. That's right. That's the problem. You wind up with, that's like saying the average weight of the suitcase is between 20 and 1,000 pounds. That's exactly what he winds up with. You just don't have the information to get a usable estimate. In October of 21, 2 weeks ago, there was an article in The Economist that's on Canvas. If you downloaded or if you looked at those articles before 2 weeks ago, this has been added. I added it on October 16th. So if you looked at all this at the beginning of the semester, this is another article that's up there. Yes?
So question, so in Union Square, there's that big clock,
Mhm.
The countdown, what does
Right.
that have to do with, like, any of this?
I forgot what that's based on.
Isn't that the debt?
Is it the debt?
Is it the debt ceiling?
It is.
Yeah.
But it's based on, they're using point estimates of the rate of growth of the debt. It's not a confidence interval, it's just a point estimate. And of course, the impressive part is it's changing from minute to minute, but that's a point estimate, okay? So in this article from a couple of weeks ago in The Economist, they talk about, given the expectations of COVID becoming endemic, like the flu, which, everything you're reading in the last month or so is now saying that. Countries have given up. I think the only country now that has not given up on the concept of eradicating COVID is China. Australia recently, Australia, I'm sorry.
New Zealand?
Australia, New Zealand, yeah, I'm sorry, I think it's New Zealand, gave up on that idea. Despite their remarkable success for much of the pandemic. So the expectation now, and of course that can change, but the expectation now is this is going to become endemic, that we're not going to be able to eradicate it, in part because of the inability to get everybody vaccinated, in part, and as a result, the variants that emerge. So it's really not going to be possible. And what they talk about in the article is they have a picture of 50% and 95% confidence intervals on expected excess deaths due to COVID. So they're not talking about tracking just the COVID deaths. They're talking about the excess deaths. In other words, taking into account that there are people not dying of other diseases because they're not getting the flu, they're not going out as much, et cetera, et cetera. They're not driving as much, there aren't as many automobile accidents, all of that. And you see in the article that excess deaths track official deaths, but there's a lot of uncertainty in there. We don't have perfect information. All right, so we understand the concepts in calculating a confidence interval. What we are going to talk about next is what everybody keeps raising, but we don't know sigma. What do we do? So our next step is, how do you calculate a confidence interval when sigma is unknown? And we're going to just start talking about that very briefly, and we'll do that next time. If you don't know sigma, you don't know that the sampling distribution is normal. That's what you lose. So, if we don't know sigma, how do we form a confidence interval? Well, it turns out that while the sampling distribution for X bar isn't normally distributed, it does have something called a T distribution, the student's T distribution. And I'll talk about why next time, how that came to be, how was that developed, why is it called the student's T distribution? Not because it's a student. That was really just a pseudonym, because the person who developed the T distribution for commercial reasons, wasn't permitted to publish his results and could only publish them with a pseudonym. And we'll talk about that situation next time. And what it says is, if your individual values are normally distributed, we didn't have that before. If we knew sigma, we didn't have to make any assumption about the underlying distribution. If you don't have sigma, you can only form the confidence interval in this way if the underlying individual values are normally distributed. So you need a lot more information. X bar minus mu over S over the square root of n. We don't know sigma, we're gonna use the sample standard deviation as an estimate. And we say, unlike X bar minus mu over sigma over the square root of n, which has a z, a normal distribution, this has a t distribution with n minus 1 degrees of freedom. There's an additional parameter that we're going to talk about, and that's the degrees of freedom. So this will enable us to form confidence intervals for the more reasonable case, the more common case, the more realistic case, when we don't know X bar and we don't know sigma. What do you do if you don't know sigma and the underlying distribution is not normal? Well, we'll talk about that later, but there are two things. Number one, in all of these computations, the normal requirement is a very robust one. If we vary from normality by a little bit, it doesn't change the results. Well, that's a very nice property. I mean, that's what makes statistical inference so powerful, that even if you don't conform to that assumption of normality, you still get reasonable results. What if you're off by a lot? Like you have one of those well-shaped distributions where you don't have the data in the middle, the normal distribution doesn't hold at all. These procedures don't work. There's a whole branch of statistics called non-parametric statistics that's used when you don't have the assumption of normality. All right, so we're not going to talk about that, but you certainly should be aware of that if you happen to be working in any areas where you can't assume normality. So there is a whole other branch of statistics that enables us to do things like this, not with as much certainty, all right, but you work with what you have. All right, so the homework for next time, chapter 8, the problems on the confidence intervals using the normal distribution. So 8.2, 8.9, that's it, 8.2 and 8.9, and a write-up on using the normal distribution. I'm sorry, I said 8.9, it's 8.10. No, 8.9. Yeah, it's just the first two on the syllabus.
And right up on what?
Right up on normal. All right, so I'm sorry, right up on confidence intervals. Yes, I gave you normal. We handed normal in today. Sorry, right up on confidence intervals. Thank you.
What about our homework, 8.2, 8.9?
The first two problems, 8.2 and 8.9. Yeah.
Can I say freely that I actually enjoy the stats class in person than the Zoom? And is it a possibility that we can have that till the end of the semester in person?
You got to talk to Farouk because that's a scheduling issue. I think the problem is that the Sunday that I'm now on, instead of that Saturday, remember there was a switch, that Sunday is a virtual day. So your classes that whole day, they're not having anything at school on that day. I would be more than happy to have all in-person classes. There's no question. You know, I mean, I'd be more than happy to. But I think that's the problem with the November 14th, and I hope that's our last virtual class.
Yeah.
Good. And we'll presentations on the 14th as well. Okay, so I'll